let me get started. According to my devices, it is now 3 o'clock. I'd like to get started today because we have, I want us to try to do a practice midterm towards the end of this class. So I want to go through the material a little bit quicker. But first of all, are there any questions about anything technically? Last class I talked about heaps and priority queues. I didn't get to go through it as thoroughly as I might like, but what you should be able to know about a heap is that it's an example of a priority queue. Priority queues are important abstractions for building algorithms around, and that heaps, you should understand why it is that heaps let you insert new items in log n time, delete the minimum item in log n time, and find the minimum item in constant time. And so I encourage you, at that level, I want people to understand what was going on. There's some fancier stuff in the lecture notes that I'm not going to have time to talk about. But that's the stuff that's important. Any questions about heaps from last time? Okay, how many people hear what I'm saying? I always get nervous until I see some twitching. But take a look at this, and we will. Okay, fair enough. And if possible, turn on your cameras because I do like to see people moving. Okay. Any other questions? The homework 1 should have begun in today, which is good. Homework 2 is going out today. And in particular, the real midterm is a week from now. And it's going to include problems from the first 4 chapters, including sorting, which is the 4th chapter. And homework 2 has the problems on sorting. So I strongly encourage everybody to do the part of homework 2 related to sorting problems before the exam. Okay, that's a good way to study. The best way to study in here is to do problems, understand why, beat your head against these kind of problems and stuff like that. Any questions? The midterm's a week from now. I gave you a sample midterm from a few years back on my webpage. It'll show you that there is a part that's going to be multiple choice. There is going to be a part of where there's going to be roughly 3 homework-like algorithm design problems. And this is going to be a little bit multiple choice is good to do remotely on, Blackboard. Typing in the solutions to algorithm problems may be harder, and that's something that we'll have to see how this goes. But I want you to be able to prepare to do homework-like problems for the exam. Any questions? Okay. No further questions on that. Now, just because I want to keep moving, I want to talk about the problem of the day. And this is a problem on sorting. And it asks whether, I said, I'm giving you 2 sets. Okay, one is of size M, one is of size N. Okay, and I want you to tell me whether they are disjoint, meaning they have no element in common. Okay, so I'm giving you, if you think of it, an array of M numbers and an array of N numbers. And I want to know whether or not I want an algorithm that runs fast in terms of M and N. And I am going to say that we know that N is bigger than M. And maybe, well, let's say greater than or equal to it is fine. But possibly a lot bigger. Okay? How can we take these 2 arrays, let's call them A and B, the arrays A and B. Can anybody give me an algorithm for testing whether or not these 2 sets are disjoint? Meaning having no element in common. Any ideas?
Yeah.
Okay. Go ahead.
Okay.
So what you could do is you could start by, like, if you don't know the sizes, you could first start off by checking them, which would be constant time. And once you
Well,
know
when you
the
say you
size,
don't know the size, okay, you're saying
but
that typically, how do you know how many elements are in an array? Someone had better give you a count,
yeah,
because you're never going to figure it out by looking at the array, right?
yes, exactly.
So, okay, you've got a counter, and you can say you can figure out which one, you know, the size, the number of elements in each array, so you know which one has n elements and which one has m elements. Now, what are you going to
Yes.
do?
So what we would do is we would sort the smaller array, which would be, in this case, it would be m log m
So
time.
you're going to, one possibility is you sort the array A, which is the smaller one. Then what are you going to do?
Then we iterate through the larger array. And for each element in that, we do a binary search on the sorted array
For
to
I
see if it's
equals
there.
1 to m, what you want to do is to search for what I gather you're telling me B of I in A. Is that what you're telling me?
Yeah, we perform a binary search on the sorted array using the elements of the unsorted array. And if we
Okay.
find any element that is there, then we know it's not disjoint.
Okay, fair enough. Does everybody kind of get that idea? Okay, what is the running time of this algorithm? How much time did it take to do the sorting?
So the sorting is m log m, and then the searching for each element is n log m.
This is n log m. So the
So
total time is something like n plus m log m. Is that right?
yes,
And since we know that n is bigger than m, what do we know about n plus m? If we want it in a big O world. If n is bigger than m, what is n plus m in a big O world?
N.
It is order n, right? Because n plus m is less than twice m. Twice n. Does everybody kind of see that? So this is giving me a big O of n log m algorithm. Is there any other way to find whether or not the two sets are disjoint? Someone want to propose another algorithm?
It's kind of similar. It uses, I guess, the same concept where you just insert them in a binary search tree and then search that way instead of with a sorted array.
Okay, so you're saying you're going to build a binary search tree. Are you going to build the binary search tree out of the elements of A or the elements of B?
The elements of A, since it's smaller.
Okay, so he's saying do that on the order of what you call it. He did that on, so he did the, you're saying build a binary search tree on the elements of A, and that you're telling me that that's still going to take m log m.
I
Because,
believe
right,
so,
because
yes.
there's m elements, you're going to insert them one by one into the tree. It's going to take log m. And then you're going to do a search, and it's going to take log m per search.
Yes.
Okay? So I think yours would take exactly the same amount of time. Is there any other way to do this?
Yeah, so I was thinking you could do it where you take the elements in the smaller set, so A, and you would insert them into a dictionary, and then you would iterate through B and then just check if it's in that dictionary.
That sounds exactly like the one with the, what you call it, with the binary search tree, using the balanced binary search tree as a dictionary.
I mean, potentially if you use the hash table, it would be slightly
Okay,
different.
now this person is talking to me about what you call it. He says another possibility is you build a hash table. And now what you're going to say is you hash all the elements of A, okay? You then go one by one for all the elements of B, and you look to see if it's in the hash table, right? And if you do it that way, you're going to build a hash table on A. So you want to say build a hash table out of the elements of A, and that should take order m time, right? And then for I equals 1 to m, okay? Actually, 1 to n, excuse me. Okay, what you would want to do is to look it up in the hash table, right? Search for B of I in the hash table. Okay, and if you're lucky, that should take constant time per element you search, and that would go around n time. Does everybody see that that algorithm is going to be order n plus m expected time? Okay. If you use a hash table, that's what you should get. Now, of course, did I say in here I wanted expected time? If I don't say anything, I mean worst case time. So if you ask me, this is one that I am not happy with if I'm asking for worst case time. On the other hand, in practice, this is probably going to be a good thing, okay? Basically, because again, unless the hash table did something bad, like put everything in the same bucket, this is going to be linear time, okay? So I want to say that in practice, this is a good thing. And, you know, I commend you for coming up with a good algorithm for this in expected time. On the other hand, if I'm looking for worst case time, I look to take off points, okay? Any other ways that I could do this in efficient worst case time, though? Is there any other ideas for how we might do this in good worst case time?
I have a quick question about the hash table idea.
Yeah.
For our expected time, would we say like it would be O of n since n is greater than m, or would we write out like n plus m?
Okay, so so let's just put it this way. The same reason why I turned n plus m to n here, because I know n is greater than m. In fact, you could get away with saying order n expected time here. Okay, when I get to graph algorithms, you'll see me write n plus m a bunch of times, and there's a good reason for that. But the same argument that I said before holds. This is really going to be order n time, the size of the bigger set. Okay? Expected. Is there any other better way to make a better worst case algorithm, though? Okay. What if I do the opposite, and instead of sorting A, I sort B, and I reverse these two? Let me now use my powers of my pen. What if I now sort B? What is the time it's going to take to sort B?
N log
Do you
n.
think, does it make a difference which one I do here? Sorting B was going to be n log n. Oh, actually, okay. Suppose I now could search from 1 to m of in this one, where I now search for a sub I in B. What is this algorithm going to take? The first part was n log n, right? The second part was m, so this is going to be n log n plus m log what?
N.
M log n, right? So this is going to be m plus n times log n, okay? Which is the same as what you say, n log n, by the same argument that we had before, right? Which one of these two is better? This one or this one?
N log m.
N log what?
M.
M. This is the winner. Why is this the winner? What
Because
if
we know
M
m is small.
was 1 and N was N? What if the smaller array had only one element to it, right? That's perfectly allowed here. And if so, this would be order n worst case, and this one would still be order n log n. So does everybody see that, in fact, sorting the smaller array turned out to be the win? Okay. Any questions about this? Any questions about why this one is better than that? And why hashing gave us a linear expected time algorithm, okay? And why the expected time algorithm is not a good worst case guarantee, but is a good thing in practice. Any questions?
I think that if we sort both arrays, we can just look through the arrays depending on which we can have like 2 pointers, each pointing at the start of.
Okay, so you want to propose yet another algorithm. You want to say sort A
And B.
sort B, and then basically walk along the two of them.
Yeah.
Like you're basically doing what's essentially the merge operation of merge sort, okay, that we're going to talk about very briefly today, okay? So that, and then you would basically, I'm still going to say basically merge, okay? Walk through them. The merging should take order n plus m, because you're going to look at every element basically a constant amount of times. This is going to be n log n and m log m. What is the running time of this algorithm going to be? I agree it's correct. What would this algorithm be? What's the running time? Somebody?
N log n.
N log n. So this one is no different than this one. Does everybody kind of see that? But sorting the smaller array and then doing the searching proved to be a better one. Any questions? See how we got that? Okay, how we did that analysis and everything like that. Any questions?
Wait, I just have one question.
Yes.
So for hashing, would the best time scenario if n was greater than m be the same exact time complexity as the worst case?
What was the last line you said? I got confused.
Would the best case be the same thing as the worst case if n is greater than m for hashing?
Would the best case be the same as the worst case for hashing? The answer is no. In the best case for hashing, all the items got spread out equally in the buckets. Bunk, 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 bunk. And so when you did a search, you were going to go find it in constant time because every linked list was going to be of size 1. The worst case time for hashing would be you use your hash table and everything happens to go to the same bucket. Now you've got a linked list of size n to go through. Each one of your is the next item in here reduces to searching in a whole list. It could that one would be an n times n algorithm. The worst case for the hashing one is actually going to be order n times m. Because if everybody got stuck when you hashed them in the same bucket, each one of the searches for the other elements is going to be a search through a whole linked list, okay? And that would be order m. Hopefully we're not that unlucky, okay? But that's why the worst case is different than the best case. Is that clear?
That makes sense. Thank you.
Any questions? Okay. What I'd like to now do is to talk about a couple of different sorting algorithms that are important to understand or know about, again, for the principles of them. Merge sort, I'm going to try to talk about so fast it's going to make your head spin, because I do want to concentrate on Quicksort today as having a different lesson. But merge sort is a algorithm that is based on a idea of algorithm design called divide and conquer. which is that I try to solve a big problem by breaking it into two smaller problems, solving them recursively, and then combining the solutions to get what I want. Okay? And with merge sort, the idea would be, if I have an array of size, length n to be sorted, if I sort the first half and I sort the second half, then I could kind of merge them by walking along the arrays. Okay, actually, walking along the arrays, starting at the head of each sorted list and finding the smallest and keep peeling them off to merge them. Okay, once this is sorted and this is sorted, the merging is actually pretty quick. And so I end up getting a algorithm that is good. Any questions with that idea? So merge sort basically looks like this. If I want to do a merge sort, okay, of an array, S, okay, and I want to merge the array, okay, I'm going to find what is the middle element of the array, merge sort the left part, merge sort the right part, and then merge then take these two sorted parts and merge them together into one sorted array. Any questions? Does everybody see why this is recursive? Okay. Merge sort is calling merge sort and merge sort. But on each, to solve it on something of n elements, okay, it's reducing it to two things, each of which have n over 2 elements. Any questions? Okay. Now, the efficiency of merge sort is going to come from the fact that if I give you a sorted list on n over 2 elements and another sorted list on n over 2 elements, we can merge them into sorted order in a total of order n time. Okay? Why is that? And this was hinted at again by one of the students on on the daily problem. In some sense, we're going to keep a pointer to the head of the two lists. And we're going to ask ourselves which of the two has a smaller value. That's one comparison. And I can decide that 4 is the smallest value overall. Then I'm going to bop this pointer up to the next element and compare which is smaller, the head of the first list or the head of the second list. Now it is the head of the first list. So I'm going to bop my pointer over and say which is smaller. Compare the head of the second list to the head of the first list. Okay, bop my pointer up. Does everybody see that every comparison, I'm getting one sorted element out for doing a constant amount of work? At the end, I want n elements. So that's n times that's order n time. N times a constant. Which is smaller, what A's list is pointing to or B's list? It's A's list. So I'm going to make that and bop my pointer over. Which is smaller? It's on what's A's list. I'm going to bop my pointer. Which is smaller? It's what's on B's list. Which is smaller? It's what's on B's list. Oh, I'm done. Now I only have one pointer. Let me clean out that array and it's done. Does everybody kind of see that? Any questions about how I can take two sorted lists and merge them with a total of n elements? They don't even have to be split evenly half and half. If I have two sorted lists with a total of n elements, they can be merged in order n time. Any questions about that? if so, what is the running time? And this is, again, how I do a merge. It's a little bit clumsy code, but it basically describes what I said before. I don't want to review that. I do want to, though, tell you, make sure you understand why merge sort is going to be order n log n. Okay? And this is something that that is a kind of analysis that you know, there's a couple different ways of looking at it, but I'll show you how I like to look at it. Okay? One thing to think when you have a recursion is to look at what does the recursion tree look like. Originally, we had the merge sort of n elements. That was this top array. And to do that, we split it into two halves. And to solve this half, we split it into two halves. To split this into, we eventually kept splitting it down until each element was its own list. If so, if you have a one element list, it's sorted, right? So at that point, we're done. And then we would do the merging up the tree. Remember, think about how the recursion is going. It says, oh, I want to divide this. Okay, start by calling this. Start by calling this. Start by calling this. Start by calling this. Then this, merge this. Then this and this, merge this. Merge this. Compute the neighboring here. Do that, merge this and this to get this. Then start over here. Pop, pop, pop. You have to understand the flow of what's going on in a recursion. But it should be clear that the operation, that what's happening in the recursion is a tree of height. Well, what's the height of the tree?
Log
How
n.
many levels can we call this recursion if we start with n elements? Okay, I'm seeing some people say log n. Why is the height of this tree log n?
Because you're starting from n elements and you're constantly breaking them into halves.
I'm dividing it. The size of the largest chunk is shrinking by a half every time I do a recursion. Isn't that right? How many times can I have n things till I get down to one? Log n. So it should be clear the height of this tree is log n. How many nodes will this tree have? Let's think about that. How many nodes will this tree have?
N log n.
Nodes, n log n. That's not, no.
2 to the n plus 1.
Okay. It's going to be 1 plus 2 plus 4 plus 8, dot, 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 up till log n, 2 to the log n, right? Does everybody agree every node, the number of nodes doubles at every layer? What is the 2 to the log n? Does anyone know what 2 to the log n is?
N.
2 to the log n is n. So this is going to be n. What is the sum as I goes from 1 plus 2 plus 3 plus 4 up to log n? Okay, up to basically n over 2. What is the sum of this going to be?
2n minus 1.
I claim that if we look at it, it's like here I've got, right, here at n minus 1, if this is n over 2, n over 4, n over 8, n over 16. Does everybody agree that always having things doesn't quite fill up the other half of an n over 2? Okay? Basically, the total number of nodes in this tree is going to be 2n, of which n of them are going to be leaves. Any questions? That's if the tree is really of height log n. If it's log n minus 1, then maybe it's only n. Okay? No, I've got to have n leaves. So yes, so this is going to be 2n. Any questions? Okay, what is the running time of this algorithm? I want to look at how much work am I doing on every level of the algorithm. at the end, this thing, where I take this array of size n over 2 once it's sorted, and this array of size n over 2 once it's sorted, how much time, many comparisons will it take to merge those two n over 2 elements into n over 2 element lists into one list of size n? I claim it will take, I'm going to say here, I'm being precise, n minus 1 comparisons. Notice if I have two elements, one on each list, how many comparisons do I need to decide who's first or last? Only one, right? If I'm only comparing two elements, it's one comparison to decide whether they're like this or like that. Okay? But how much work is done on this level to take the n over 4 elements here and the n over 4 elements here and merge them into a sorted list of size n over 2? Does everybody agree that the time it takes to do the merging is proportional to the number of elements there? So this n over 4 plus this n over 4 gave me n over 2. This n over 4 and this n over 4 gave me n over 2. The total amount of work is going to be, okay, 2 times n over 2 comparisons, which is again roughly equal to n. What about the next level? To do the merging of these 8 regions, each of which is of size n over 8, into regions of n over 4. This is going to take n over 4 steps. This is going to take n over 4. That's going to take n over 4. That's going to take n over 4. Does everybody see that 4 times n over 4 is n? 2 times n over 2 is n. 8 times n over 8 is n. The total amount of work done at each level of this tree is going to be order n. And if we have log n levels and n work per level, that would be n times log n, which is, again, O of n log n. Any questions why Quicksort, my merge sort, is an n log n algorithm? You should see where the log comes from, which is what we get by the number of levels, and see that I kind of counted the work by saying that the total amount of work done on any level is O of n. Okay, and if you believe those two things, you believe merge sort is n log n. Any questions? Any questions about merge sort? So that's one, and that's in my mind the most elementary way to see that merge sort is n log n. The other way to see it, which if you took AMS 301, you may know about recurrence relations. One way to think it, if T of n is the time it takes to use merge sort on n items, I claim that the time it will take is 2 times the time it takes to merge sort on half the items, plus another linear amount of time that is spent doing the actual merging. Okay, that you get a recursive equation that the running time of Quicksort, of merge sort, is T of n is twice that of sorting something half as big plus order n. This recursive equation happens to be solved to be theta of n log n. Okay, and many algorithms classes will teach you a lot about solving recurrence relations and things like that. I don't want to think about that too hard in here. I like the understanding why the work is coming from adding up the levels. But if you know about recurrence relations, this is another way, or if you read in the book about it, this is another way to get that n log n bound. Any questions? Any questions about merge sort? Going once, twice, sold. Okay. Merge sort is a great example of a divide and conquer algorithm. Quicksort is kind of a divide and conquer algorithm, but in fact it is more interesting to be thought of as a randomized algorithm. Randomized algorithms are very important and interesting things, okay? So like merge sort, Quicksort is going to sort n things by breaking the problem into two smaller problems. But it's going to do it in a different kind of a way. When you ask Quicksort to sort a array of size n, we're going to pick out one of the elements, okay, and we're going to use that as our pivot element. And then go through the array and place all the elements that are less than the pivot on the left side. That's bunk, bunk, bunk. Take all the elements that are greater than the pivot and put them on the right side. Here, bunk, 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 bunk. If you've done that, there is exactly one spot in the array, and that's where we're going to put our pivot. Okay? So Quicksort is going to do is we're going to pick an arbitrary element as a pivot, then partition the elements into those that are less than the pivot and those that are greater than the pivot, and put the pivot element in between them. Okay? What is interesting about this procedure? Okay? The interesting thing is that the pivot is going to end up in the exact right place where it should in final sorted order when we sort the array. Why does the pivot have to end up where it is now?
Haven't you been counting like every single time that you found a value that's less than the pivot? So you would just increment that index by 1, and then you would place that pivot in that spot?
Right. So one thing you could say is that if you want to know where the pivot ends up, you could go through the array in linear time and count how many elements are less than it. And that would tell you where it's going to end up. But that's why after you've done the partitioning, it's going to end up in the right spot. All the elements that are less than it are exactly the ones that are to the left of it. None of the elements that are greater than it are going to be to the left of it. So it's going to get into the right position. Okay? So the interesting thing about Quicksort is that after we have done one of these pivoting steps, these partitioning steps, we have broken the array into two different halves. There is a left part and a right part. The pivot is where it is. If I want to finish sorting the thing, all I've got to do is sort the left part and sort the right part. And I can do that recursively. Any questions about the pivot operation here, the partitioning operation? Okay. Any questions?
Could you clarify a little more on the idea of internal versus external sorting?
Okay, you're saying that there was a slide I blew through because I'm running slow on the difference in external and external sorting. The sorting, when you write a sorting program, it's something that's running in the main memory, the RAM of your computer. Now, suppose I ask you to sort the internet. Okay, Google sorts the internet. Okay, There is no computer around with as much RAM as there is the size of the internet, okay? So it's got to kind of store data on disks and find a way to sort the data. The data's going to sit on disks, move it around the disks so that it becomes properly ordered. If you're dealing with a big enough problem that you're accessing the disks, that becomes an external memory sort. Okay, and this is a somewhat different kettle of fish because disks are slow to access, and you want to access your data in big chunks. Okay, that turns out to be why merge sort is a good thing for big sorts that are going to involve using disks. Okay, but I don't really want to talk about that more. I want to talk about the idea of you know, what you call it. I wanted to use the idea of how quicksort and merge sort work. Any questions? Okay, let's go through this one more time, a little bit more carefully. How do you go about doing the pivoting, the partitioning? Well, if I know what my pivot is, if I have an array here of elements, and again, it's just a coding trick to how you do it. Certainly, if I had an extra array, I could go through, once I know what my pivot P is, I compare the first one. Are you less than the pivot or greater than the pivot? If you're less than the pivot, I'm going to put it in here and keep a pointer to the next spot. If you're greater than the pivot, I'm going to put you here and keep a pointer to the next spot. This one, less than it, put it there and bop my pointer up. It should be clear that I am I'm comparing you against my pivot and putting you on the right side in constant time per element. And, you know, if there's n elements, doing the partitioning is going to take order n time. Okay? It's linear time because I can do this in a constant time per element. And again, there's a little bit of intricacy in doing it so I don't have to use a second array, but that's just a coding trick. Does everybody agree that I can take an array, pick an element, and then in order n time, put the elements less than it to the left, greater than it to the right, and put this guy in the right spot, the pivot in the right spot? Any questions? Everybody should believe that, or they should question me. Okay, good. Now, what is great about the pivoting is the partitioning takes order n time. Once we've done it, the pivot is happy where it is. The left elements, all the elements on the left of these are all less than the pivot. All of these guys are greater than the pivot. That means that in sorted order, none of these guys are going to swap sides. Therefore, I can sort this guy independently and this guy independently. And once that's done, then I have the array completely sorted, and that gives me a recursive sorting algorithm. What is the implementation of Quicksort? It is recursive. Quicksort calls Quicksort. It starts by saying basically, pick a pivot element, okay, and partition the array into the stuff to the left of the pivot, the right of the pivot, and give me P as the position of the pivot. If so, the left half of the array goes from L to before the pivot. The right half of the array goes from after the pivot to H. Sort those recursively, and I'm done. Any questions about that? Does everybody see how Quicksort is written? The partitioning operation is a little bit clumsy, but it's not that big deal. This is something you should be able to figure out how that works, okay? You should see that this is going to be an order n algorithm. If I believe that this is going to do the pivoting, notice it's got one loop, and in between it's just doing a constant amount of work, doing a comparison, swapping an element, popping a pointer, okay? I claim that the partitioning is going to be order n, okay? And then we have to recursively sort the two half chunks of the array. Any questions? Bing. What would be the best case time for quicksort? The best case time for quicksort is going to look a lot like merge sort. Okay? If we want a divide and conquer, okay, if you want to do the minimum total work in a divide and conquer, almost always the right thing to do is for, to divide the problem into two equal parts. Okay? If you and your, you and your partner wanted to get the homework done as efficiently as possible, some of you may have said, let's divide the problems among them. Should you have divided the problems equally? Okay, or should you have given one, you do one and the other guy does all the rest of them? If you want to minimize your effort, I guess that's the best way to do it. But the most efficient way in general would be to divide it equally. Of course, the best way to do the homework so you learn something would be that all of you sit down and try to do all the problems and argue about them. That's the right way to do it. But for a divide and conquer task, the right thing to do is to divide it equally. If you got lucky, the pivot element you picked would sit exactly in the middle. If the pivot element sits exactly in the middle, the job of sorting the two arrays is going to be twice n minus n over 2, which is exactly what we had recursively in merge sort. The same thing is going to happen. We're going to get a division where we start out with an array of size n, and after one partition, each one of the biggest subarrays are of size n over 2. We then divide these n over 2, and if we get lucky with the pivot, it will end up in the middle. The pieces we get are of size n over 4, ... How many layers do we need if we get lucky with every partition? How many layers do we need till we get every element down to an array of size 1, which is sorted? How many times? Seeing log n's lighting up the chat, okay, because that's the right thing, okay? How many times do I have something till I get to 1? So if the pivot element was perfectly the median every time, it's clear quicksort would always be n log n. But we don't know that, right? What is the worst thing that could happen if you did this quicksort algorithm? You pick a pivot element and it happens to be the first one in sorted order. When you did the divide, because it's first in sorted order, the left subhalf is in fact going to be empty. Then goes the pivot, and then you've got n minus 1 elements to sort. Does everybody agree with that? I'm now down to this layer of the recursion. What if you got unlucky and then picked as your pivot the smallest element again? How big is the next element? You're going to pull off one element from the biggest thing. What if then the next level you don't pick the first element, you pick the last element? That's no different, right? You're going to have one element in a pivot, one empty array, and n minus 1 other things. What is the height of this tree going to be? Okay. If you're peeling off one element per layer, it's going to be something like n minus 1 or n, big O, it's either n minus 1 or n. Okay. But it should be clear that if you're unlucky, each, your tree is of height n, What's the amount of work done in doing the pivoting? We had to compare the partition. You compared the pivot against every single guy in the array. It took order n. If you got unlucky, you spent order n time and learned almost nothing. And if you do spend order n time, n times, that's n times n. In the worst case, Quicksort is going to be n times n or n squared. Does everybody see that? Any questions about why Quicksort, if it is bad, is n squared? Okay. And does everybody see that it kind of depends upon what you're given as an array, whether you're going to get lucky or unlucky? Okay, you can't kind of force your luck on this. Okay, any questions? Okay. But what's going to happen in the average case? And this is where the magic of Quicksort and randomization comes in. What if I pick my pivot element? It's going to be one of the n elements in my array. Suppose I pick it at random. Suppose I say that a good pivot is one that appeared between n over 4 and 3n over 4 in sorted order. The median was our dream pivot. When we're doing Quicksort, we're dreaming, praying we're going to get the median. But what if I say a pivot element is good enough if it happens to be the one that is in between the, is in either the second or the third quartile in sorted order, right? What is the probability if I pick an element at random out of n elements? It's going to lie in the second or third quartile. Somebody with a voice?
0.5.
What?
0.5.
0.5, it's 1/2. Why? Because if you notice, the size of the second quartile and the third quartile is just as big as the first quartile and the fourth quartile, right? Half the elements make pretty good pivots, okay? In fact, notice that if you pick the worst possible pretty good pivot, it's good. Let's say I picked this guy as my pivot. What is the size of the largest array going to be after I've done that? What's it going to be? It's going to be at 3/4. I will have at least split off 1/4 of the elements in one. I didn't just take off one element, I took off 1/4 of the elements. I've made progress, even if I picked the worst possible pivot. I've made pretty good progress. Does everybody agree with that? Okay, so there are a couple different kind of hand-wavy ways to see this. One thing is to notice, suppose I picked an element at random here. What is the expected size of the largest piece? I claim because there's just as many worse pivots of this as there are better pivots of this, okay? I want to argue that, let's say we always picked the worst possible good pivot. How long would it take under those conditions? Okay, what would the tree look like? I claim that at the first level, I would end up with 3/4 n and 1/4 n. Does everybody agree with that? Next time I split this, what's going to happen? I'm going to get 3/4 of 3/4 n is going to be the biggest one. That's going to be 9/16 n. The next one is going to be 3/4 times that. In general, okay, I'm going to be, the biggest piece I'm going to have is going to be, if you want to, is going to be always 3/4 the size of what my previous thing is. Okay? What is the number of levels? If I start out with n things, and at every level I don't have it, but I 3/4 it, what is the number of levels until I get down to 1? It should be, I want to know, what is the value of L, n, times 3/4 to the L till I get to 1. What is the number? That's going to be the number of levels. If I always pick my worst possible good pivot, or the kind of expected value that I get at each time. What does that mean? Well, if I rearrange this equation, I claim that this, if I rearrange this equation, what I'm really getting is that n is equal to 4/3 to the L. How do I solve for L? What is the height of this?
Take the log of both sides.
Hit it with a log. What is that going to be? Log, let's say take the log base 4/3 of n. What's the log base 4/3 of 4/3 to the L? That's L times the log of base 4/3 of 4/3. What is the log of base 4/3 of 4/3? More generally, what's the log of A base A?
1.
1. So this gets blown away. The height of my tree is going to be the log base 4/3 of n, which is theta of log base 2, right? So what I'm going to be getting when I do a quicksort, okay, is something where I'm occasionally going to have a lousy pivot, okay? This was a lousy pivot. I'm occasionally going to get a good pivot, okay? A great pivot. That was a great pivot, right? Okay? In average, I'm going to get one that's going to split it 3/4, 1/4. And so the height of my tree is going to be log base 4/3 of n. And since I still do, by the same argument as before, I still do order n work per level in my partitioning across all of these guys. Okay? Am I going to get a situation where the expected height of the tree is going to be log n, and the work done on every level is going to be order n? So what I expect is, on average, the expected time is going to be n log n. Any questions about where the n log n for quicksort comes in? Okay. If I'm picking this thing at random, what's going to be happening? Okay. Pick it at random here. I might pick, let's now get another color. What's it? Blue. I haven't used blue for a while. That's exciting. If I pick pivots, what's going to happen? Boom, 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 boom. Does everybody agree? Half the time I get a very good pivot. On average, I get a pivot that does as much work as this. What happens if you're standing next to you have a guy who, when they do quicksort, they pick a pivot at random, they pick this, then 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 they pick this. If they were picking this at random, what do we know? We know they are very unlucky people, right? Are these people you want to stand next to in a lightning storm? You do not want to stand next to these people. Does everybody kind of see that? It has reduced the problem in order to have it get the bad case. If you're really picking the pivot at random, then you've got to be unlucky every single time. Okay? And nobody gets that unlucky. Okay? That's why Quicksort will run in n log n time very reliably. So reliably that it is in fact the fastest of the internal sorting algorithms. Any questions about that? Any questions about why Quicksort is n log n and why it is a randomized algorithm? If we pick the pivot element at random, we're kind of tossing coins. We're using random numbers to tell us where the partitioning is. Again, you can make everything I said more formal and do math, but I don't want us to think of it that way, and I don't think you do either. Any questions? There is a very important punchline here that I want to say, and then we're going to move on, okay? The important thing is, why is randomization such an important and wonderful idea? If we pick the pivot element at random, there is not a worst case for this algorithm. This is kind of an amazing thing about it. Let's say you go to the Trump and Biden are about to have a big debate, okay? You could imagine one of them complaining to the other one about being wasteful of government money. One of them brags, when I was in office, I got everybody to use randomized quicksort, okay? Now, I got everybody to use quicksort. Well, if they didn't pick the pivot at random, maybe always pick the last element of the pivot as the partition. Then you could imagine the opponent pouncing and saying, well, what if I gave you the case where they were already sorted? Okay, you're going to pick this guy as a pivot, and it's going to do no good. And you're going to pick the last element as the pivot, and it'll do no good. Does everybody agree that if you pick the pivot partition element according to a fixed rule, there is a place to put it such that you will always pick a terrible partition, right? So you can imagine if Biden is bragging about using quicksort, but it was deterministic, Trump would pounce and say, yeah, sort this thing when it's already in increasing order. See, you're being wasteful. But Biden would say, no, I didn't use a fixed partition. I picked a pivot at random. Okay, I'm going to flip coins to decide which one to pick. And now his opponent is helpless, right? There's no way he can design a bad input because the pivot that you're picking is going to be chosen at random. And now only if you are very, very unlucky will you do badly. Okay? So this is kind of an important and subtle thing. If, you just pick the last element as the pivot, what you would go and you can get a guarantee on Quicksort that said, well, if you give me the order in random order, then Quicksort will run an expected n log n time. But if you pick the elements, put the elements in a, or a fixed partition. Okay, if you pick the elements randomly, the pivot element randomly, no matter what order of input it is, with high probability, you're going to run an n log n time. Only if you are unlucky enough to repeatedly pick terrible pivot, terrible pivot, terrible pivot, will it take longer. And you can't be that unlucky, okay? Any questions about it? That's why randomization is a great idea, okay? Any questions?
Can you just really quickly go over like a few slides ago where you were doing the 3/4 to the power of L times N equals 1?
Let me just think about this. One quick question. If I asked you to push the exam back for another 5 or 10 minutes, that doesn't scare you, does it? Okay, so you wait here and get ready to start it then. Let me go through and do this very quickly. He wants to know, where did my 4/3 come from? Okay, call it a hand-wavy argument or not, but it's not, there's a formalness to it that I'm not showing you. If I pick, what is going to be the, well, let's stop and think about it. Maybe it's a little bit of a different argument, actually. What is the pivot? If I pick a pivot, I'm equally likely, what's the best pivot? Is this one. What's the worst pivot? It's that one. Does everybody see my chances of getting a pivot this bad is as bad, is the same as getting a pivot this good, right? And when I move it in, what is kind of going to be the average value of a pivot? I claim that if I pick my element at random, okay, I would expect that kind of, on average, sometimes I'll do better, sometimes I will do worse. But kind of the average power of this, you should see, is kind of going to leave where one of the pieces is going to be of size 3/4 and the other is 1/4. Does everybody see that that's kind of what should happen on average if I did this over and over and over again? Okay. Now, what do I know? What is going to be the number of levels on a tree where I partition it into 3/4 every level? 3/4 of the, if I start out with 3/4 n, if I take 3/4 of that, I've got 3/4 times 3/4 n on the next level. On the next level, I'm going to multiply it by another 3/4. On the next level, I'm going to multiply it by another 3/4. How many times can I multiply 3/4 till I get n? Okay, or more precisely, if I start out with n things, how many times can I 3/4 it till I get down to 1? What is this? Well, multiply both sides by 4/3 to the L. That's going to say n is equal to 4/3 to the L. Does everybody see this is the same thing as this? Okay, now hit it with a log base 4/3 for convenience. This is going to mean log 4/3 n is equal to the log 4/3 of L to the 4/3. That turns out to be L. So the height of this thing is going to be log base 4/3 of n, which means it is theta of log n, which means that the total work is n times log n, or n log n. Any questions about Quicksort? Anything else? Okay.